Here's an interesting problem for the strong math induction proof. Great example. We have A1 is equal to 1, A2 equals 2, and then AN plus 2, the second term is equal to the sum of the two previous terms. Sound familiar? That's Fibonacci in a nutshell. We can show that this A of n term, though, has to be less than 5/3 to the n. It's another way of thinking of a shortcut. This Fibonacci sequence and rule and relationship has so many different parameters to it that it's fun to see how they all come about. So we are going to prove this. Step 1, we'll just do the old n equal to 1 step. And the n equal to 1 step says that if we have A of 1 should be less than or equal to 5/3 to the 1. Or A1, which is 1, should be less than or equal to 5/3, which is true for n equal to 1. Now, for step 2, you're going to look at n equal to r, okay, where r is less than or equal to k and A of r is less than or equal to 5/3 to the r when r is equal to 1, 2, 3, all the way to k. So we still get this A of k thing going, but it's just a way of keeping track of not just saying this is okay for n equal to r. R has to be delineated for each of the values from least to most, and most being k. All right, then we do step 3, the favorite step of them all. N equal to the k plus 1. All right, so to do that, we're just going to do a little bit of fiddling. A of k plus 2 is equal to A of k plus 1 plus A of k. Now we're going to try to get this so it looks like approaching k plus 1. So we want this A to be k plus 1 and not k plus 2. So if I subtract a term and say A of k plus 1 will just be A of k plus A of k minus 1. Because we're trying to get this as my end result, we're going to express A of k as 5/3 to the k plus 5/3 to the k minus 1. And as best we can, A of k plus 1 is going to be 5/3 to the k plus 1. So we want this side to have a 5/3 to the k plus 1. So to do that is going to take a little bit of algebra. Not bad. 5/3, okay, to the k times 5/3 to the 1 will get me that 5/3 to the k plus 1. You can't do that unless you multiply by 3/5. Okay? Now we're going to do that with this next term. 5/3 to the k minus 1. Okay. I'm going to make that times 5/3 to the second, because that'll get me the k plus 1 that I can factor out. But I'm going to have to multiply by 3/5 to the second. Huh? Well, putting these two together, here and here, gives me 5/3 to the k plus 1. Putting these two, oops, excuse me, try that again. These two together will give me 5/3 to the k plus 1. These two together will give me 5/3 to the k plus 1. And that's what we want, 5/3 to the k plus 1. So we're trying to manipulate the shortcut to get to that. Now we have 5/3 to the k plus 1 times 3/5 plus 5/3 to the k plus 1 times 9/25. And so then when we factor out, when I factor out the 5/3 to the k plus 1, what will happen is I get 5/3 to the k plus 1 will leave us with 3/5 plus 9/25. And so we're going to have 5/3 to the k plus 1 times, let's get the common denominator of 25ths here, we'll get 15 and 9 over 25. Or 5/3 to the k plus 1 times 24/25. Now that is a little bit what to 5/3 to the k plus 1? What is it? Well, this quantity here is just a little bit tinier than, right? And so what we showed here is that this, putting these two equations together, you're going to be able to make this statement that a of n is a little less than 5/3 to the n. This is my sum, is a little less than 5/3 to the k plus 1. And therefore, true for n equal to k plus 1. And then you can do the final victory lap. Therefore, since true for n equal to 1 and n equal to r plus 1, where r is equal to 1, 2, 3, all the way to k, then true for all k greater than or equal to 1 by, I should say n, greater than or equal to 1 by math induction.